All right, the next example that we have in 16.3 is example 4, where we are asked to find a potential function for this three-dimensional vector field. So what I'm going to go ahead and encourage you all to do, um, maybe not encourage, but here's what I'm going to do. Because this problem is telling us to find a potential for this vector field, that's implicitly asserting that one does exist. It's not explicitly asking us to prove that one exists and then go find it. It's more or less telling us one exists, find it. So in that sense, I'm not going to go ahead and check the conditions for this, but you would go ahead and check these conditions, all three of them. Or it's the same thing as just showing that the curl is the zero vector. So what we did here, I just took these two and showed that they were equal. So I'll rinse and repeat that exact same thing over here. If you want to take a look at the first minute or two of the previous video, you can to see what I mean if you didn't watch that one yet. But yeah. All right, so that being said, we're just going to go ahead and get started chipping away at this. So I'm just going to go ahead and say that suppose the vector field f given above is the gradient of some scalar function f. Then this means that the x partial, y partial, z partial of that scalar function f is equal to our given vector field. So 2xy z to the negative 1, z plus x squared z to the negative 1, and y minus x squared y z to the negative 2. All right. So what I'm going to go ahead and do here is, like I did in the previous video, I'm going to go ahead and say, okay, well, the first component here, f sub x, needs to be equal to this vector's first component. That gives us the following equation. So if you want to break this up in stages, I guess we could. So step 1 is we are going to go ahead and get an expression. So get an expression. I'm going to try to make this a little bit more organized than the previous example because this is 3 dimensions. So there's a couple extra steps, and usually this is the one where it gets a little bit more confusing. So we'll start there. So we're going to get an expression for f from f sub x equals the first component here. So here I'm calling this f1, f2, f3. Okay. So in that way, we'll go ahead and say f sub x equals 2x y z to the negative 1. And this tells us that, or implies that, if we integrate this with respect to x, we should get an expression back for f. So we would have x squared y z to the negative 1 plus, and again, what we put here, it has to be able, so whatever we put in this box here, when we take the partial derivative with respect to x, it has to equal 0. So could it be just real numbers? Certainly. The derivative with respect to any variable of a true constant is 0. We could differentiate with respect to anything that contains y's. That would give us 0 with respect to x, since they're independent variables. And we could also do this with respect to anything containing z's. So what goes here in this box is going to have to be an arbitrary function of both y's and z's. So essentially, whatever this variable isn't goes here for this first round of integration. So this gives us an expression for f. Okay, so right now this is sort of like our best version of what we have for f. So let me go ahead and box this in blue, since we're going to have to come back and refer to it. This is right now the best we can say about f. We can do better, but this was our first order approximation of what f is. Now, what are we going to do in step 2 here? Step 2, we're going to set the y partial of f equal to, so actually let's rephrase this slightly differently. We are going to take the y partial of the above version of f and set equal to the second component of our vector field, f2. All right, so del y of, I'm just going to grab this expression right here. So the y partial of that has to equal the second component from above. So we're going to have z plus x squared, z to the minus 1. All right, we can go ahead and take our partials on the left. So this will be x squared z to the minus 1 plus, now because this function g does have both y and z, it has two variables, I'm not going to use the prime notation that I used in the previous example when I had a function of only one variable. In that case, it's not ambiguous. It's unambiguous to use the prime notation if you have a function of one variable. But in this case, we have a function of two variables, so I'm going to go ahead and just use that subscript notation that we're familiar with. All right, so we've got something like that. And then over here, well, we're not supposed to do anything with this, but we'll just copy paste it. So just bring it down, and now simplify. Notice here that these cancel. So this tells us that the y partial of g must equal z. All right, well, this will allow us to solve for g. So let's just write that here. So we're going to solve this for g. How are we going to do that? Well, this implies if this is the y partial derivative, then integrating this with respect to y on both sides should give us back just g. So g of y and z is equal to the integral of z with respect to y, which is y times z plus, again, what are we going to put in this box? Well, because our function is of two variables, y's and z's, it seems like we have y's, z's, and numbers that are possibilities. But because it can't be y's, because if we were to differentiate it, we only want to have z come back to us. If I had a y in here and we differentiate it, then this integrand here should have been z plus 1. Because it's only z, this tells us there can't be any y's in here. So you're never going to include that variable of integration. So we basically have z's and real numbers. So the only variable is z. So we're going to have a function of one variable, z. Be sure to give it a different name, then f or g, because although h is being used to define g, h is distinct from g. They're not equal, so we don't want to say g of z. That would be incorrect. All right. So now what we've effectively done is we have taken this version right here of f, and we said, okay, we know f definitely contains this term, and we need to account for the fact that it could contain some y's and z's and real numbers here. We don't know yet what that is at this stage, but we do know that there could be something like this. All right, then we use the next piece of information. We use the second component of our vector field to go ahead and actually further refine what this is. We actually know now that this g of yz contains this term, and now we're saying, okay, now the ambiguity only lies here. So now you can see there's a trend here. What is the next thing? Well, we're going to further investigate and refine this and see what this has to contain. So what we'll do here is we'll use this to update f. So once we have this, maybe I'll make this step 3. So in quotes, update our expression for f to include the new information. So this would be f equals, what did we have before? We had x squared y z to the negative 1, and then we were adding this g of yz, but we know what g of yz is. So we can replace this g of yz with this. So we'll take that out, and we'll just put plus yz plus h of z. So now what I'm going to do is I'm going to box this in blue, because now this is our best version of what f is. So I'm going to go ahead and remove that blue box. That's not the most accurate or closest approximation. Right now it's this blue box. All right, I'll move up to the other side of the page here, and let's go ahead and do step, I guess, what is this, 4? So for step 4, we would set the take the z partial of f equal to f3. And I'm going to go ahead and put the blue box here, just to let us know we are referring to we're always going to be working with our most up-to-date version, right? We're never going to go back to all the way to the beginning. We always want to continually refine and get better and better and better answers. So that's what I'm referring to with f. Okay, so the z partial of our most up-to-date version, so let's go ahead and just grab that. And if we grab that, so this needs to be equal to the z component, which is y minus x squared y z to the negative 2. And if we take the z partial of this group in parentheses, we will have negative x squared y z to the negative 2 plus y plus h prime of z. Again, I'm going to go ahead and use the prime notation because this function h is a function of a single variable z, so there's no ambiguity here in using the prime notation. Copy paste the right hand side since we haven't done anything with it, just written it. And then we want to simplify. So everything on the right hand side cancels. On the left hand side we only have h prime of z, so we know that h prime of z is 0. Well, since this function is only of one variable, the only way a derivative of a single variable function is equal to 0 is if that function is a constant. So technically we would integrate here, but because this is 0, we know that it has to be a constant. So I'm going to go ahead and just say that this means that h of z is some constant c. All right, so then step 5 would be to write your potential function. So I guess we can say update f again. And that's the potential. So f was equal to this expression right up here. So I'll grab that. And we know that from up here that h of z is a constant. So this h of z can just be given a plus c. But remember, this right here is what I have written right here. This is a general expression for all possible potential functions, for all potential functions of the given vector field capital F. This problem, again, in the wording, all of the wordings are going to be find a potential. So since it's a potential, so I'll say in particular, a potential, and I'm going to put in parentheses here with c equals 0, is f of x, y, z equals x squared, y, z to the negative 1, plus y, z plus 0. So just that. You'll notice here that I haven't been putting the of x, y, z for all of these f's. And that's because we're writing f so many times and we know that f is a function of 3 variables. The reason why I'm writing the variables for h and for g is because they're definitely not 3 variables. So I want to emphasize what they actually are. That's all. But for my final answer, this is a formal thing, so I'm going to make it formal. So that means I'm going to include the variable statement.